Demystifying LLMs. So what are LLMs? LLM stands for Large Language Model, and these are statistical models that infer the next word based on likelihoods or probabilities. And it takes what has already been spit out and continuously infers the next word in the sequence. They're kind of like fast guessing machines. So you can see here, they take what has been previously spit out, and then they would just infer what comes next in the sequence. And LLMs have progressed a lot over the last 3 years. LLMs started out with the introduction of the Transformer by Google in 2018, and the paper was called Attention is All You Need. Since then, LLMs have started to pop up in greater density or parameters. And parameters are the number of inputs that the LLM has taken in and can handle. So it started out with Elmo, followed by BERT, which was released by Google, GPT-2, which was released by OpenAI, Megatron, Turing, and LG, GPT-3, which is released by OpenAI, Palm, which is released by Google, and the AI race continues to increase the size of the models and increase the number of parameters that they have. The larger the model, the more refined the responses that can have, but also the cost and weight of using the model is greater. As the number of parameters increase, then the LLM costs more money to run because it requires more computing power. So we're currently around 2013 and recently OpenAI released GPT-4, which has close to 1 trillion, if not more, parameters. Something important to note is that language models are not knowledge models. Language models exist only to create human-like speech, but they do not guarantee accuracy of statements. There are other models trained to provide accurate results. So what language models can do when asked a question about specific world knowledge is hallucinate. Because they're guessing the probability of the next word based on the previous word, they will just take the repository of knowledge that they've gained and then infer what the next thing most likely to be said is. So if you provide it with a series of data from other humans that basically says the best animal is cat, and you provide enough training data that overpowers the other different kinds of prompts, then when you ask the question, it will basically infer that the best animal is a cat because statistically, based on the previous information, that is true. However, that's not universally true, which is a danger of large language models and why hallucinations do exist. So be wary of what you read from an LLM. The results they spit out are just byproducts of statistics. There are a few ways you can harness the power of LLMs to create website copy or create sales pitches and perform extremely incredible human-like tasks very quickly. And those are understanding prompt engineering, priming the AI, and providing details as needed. So now let's talk about transformers and what are they? This is a very high level. I'm not going to get into the actual code and the data science about this, but I'm going to explain at a very high level what transformers are and why they're so revolutionary to generative AI. This also will give you an understanding of what's happening behind the scenes to get a grasp of when a LLM hallucinates what to do. So at a very high level, just a little history. Transformers were created at Google in 2017, and they have a system of attention. This is radically different than any other previous neural network model. And the significance of attention is that it gives different weights for each section of training data. So not everything is treated at equal importance. Some parts of the sentence and the data are more important than others. So generative AI is just a prediction machine. Inference, or predicting the next word based on your previous word, is at the heart of generative AI and chatbot technologies like ChatGPT and Bard. And compared to AI 20 plus years ago, the major difference between AI now and then is that machines are much faster and much more powerful now. And they can train models are magnitudes bigger and faster than previous models. So let's go through an example on a high level of what happens when you feed data into an LLM to train it and how it gets transformed into something that's usable and almost mimics a real person. So let's give a simple sentence. Let's say we're given a sentence like, to be or not to be. That is the question. Whether 'tis nobler in the mind to suffer, which is a snippet of a popular and well-known Shakespeare quote. So first, we need to do an encoding. And encoding is converting a human-written sentence into something that a computer can use. So we're going to be using a process called n-grams. And n-grams is just a grouping of words of quote-unquote n elements. And n in this case can be anything. And let's say it's 3. And another word for this that's commonly used in the AI space is calling these tokens. So in the previous sentence, to be or not to be, that is a question which says noble in the mind to suffer. Let's break this up into 3 grams. So a 3-gram conversion would be first taking the sentence, making it all lowercase and stripping all punctuation, and then taking groupings of 3 and repeat that for the entire sentence. So in this case, to be or not becomes a 3-gram, be or not becomes a 3-gram, or not to becomes a 3-gram. And then we continue doing this for every combination of 3 words until the very end of the sentence. So this is sort of the conversion that happens when a computer is getting fed training data and is converting it into something that can use to predict or generate generative AI responses. So let's assume that we just did this for the entire sentence and then we have a giant 3-gram list that we can use to start building our inference. So now that we have the 3 grams generated, let's build the inference matrix, which is basically taking the 3-gram and trying to take the next word. So we're basically saying that for this 3-gram, the next word will be something else. So the sentence, to be or not to be, that is a question. Let's take the first 3-gram, to be or. The next word is not in the sentence. So we have a lookup table that basically says for to be or, the next word is not. And then be or not, the next word is to. And then or not to, the next word is be. And so on and so forth. We keep doing this for every n-gram in the table. And then now we build an inference table from that sentence being trained. So what happens next will depend on what happens in the past. So if we take a look at the existing input, then we can infer what the next word will be depending on the existing input. And this is why common generative AI tools require a prompt, because without that prompt, you wouldn't really know where to start. And it's kind of like shooting darts at a dartboard. You don't know where you're going to get, and it won't be tailored in a way that you'll get an answer that's usable. So given a prompt, this acts as a seed and will start the inference cycle. So let's say we're given a prompt and we're doing a 3-gram or a 3-token LLM. And let's say we're given to be or not. The input of the LLM is now the 3-gram be or not. So now let's infer. Based on the input 3-gram be or not, we will need to infer what the next word will be. Look at the previous inference matrix, which we made here. You or not for next word, we already defined as to. So let's go forward. And now that we have the prompt be or not, to be or not, we insert to into the prompt. And then now we have created an output. So to be or not to. This is starting to look familiar. Now we don't have a complete answer yet because we haven't reached an end of input, sort of end of sentence delimiter. So now we need to keep inferring. Now, since the input has changed, we need to take a 3-gram of this input again, which is now or not to, and then we need to predict the next word. So now we take or not to, which infers based on our inference table, or not to refers to be. So we take B and put it back into the input, and we have a newly generated prompt of to be or not to be. Now, this is starting to look really familiar. So we continue this until we get to a point where we reach an end of sentence and the output is finished. But why do hallucinations happen, and why are they such a big deal? So hallucinations happen to everybody. The previous sentence is very simple because it's extremely deterministic. But let's use something that's trickier. Let's say we give it a sentence like, that's our training data, and it says Robert has a white dog, Kathy has a white cat. Going through the previous example, let's generate a 3-gram. So we generate a list of Robert has a white, which is just taking a combination of 3 words that are next to each other and doing that throughout the whole sentence. A white dog, Kathy, so on and so forth. And we keep doing this until you reach the end of the sentence. So the previous 3-gram conversion now becomes Robert has a, which the next word is white, has a white. Now the next word is cat or dog, a white dog, and the next word is Kathy. Can you sort of see what the problem might be already? I'm sure you already see something that's different about this example than the previous example. And if you haven't seen it already, I will let you know. Now, has a white is no longer deterministic. There are 2 options here, a cat or a dog. And this is a big problem, and I'll tell you why. So let's go ahead with an example, and we start the prompt with Robert has a sort of fill in the blank. From the previous 3-gram, we know that this 3-gram only has 1 option afterwards for this because Robert has a only has white as a next output. So we can take white and then feed it back into the LLM. So now the prompt is Robert has a white. So has a white is now the new 3-gram. And now there's 2 options, which makes it tricky. There's either cat or dog. And what do we do in this case? Because we don't really know what the right output is. So we flip a coin, like any practical person. And we don't really know, so we can't really tell. We just need to spit out an answer very confidently. And this is why a lot of LLMs spit out very confident responses. Because they both have an equal chance of being picked, we flipped a perfectly fair coin, and there are 2 possible outputs. Let's say we pick dog, and the output is correct. So we have Robert has a white dog. This is the right answer. However, let's say we pick cat. Now we say Robert has a white cat. This is not correct. And this is the core problem of LLMs. In the case where the output isn't deterministic, it might pick the wrong answer, but it won't tell you that the answer is wrong because it doesn't know. Therefore, the hallucinations act very confidently and can give you incorrect answers. So LLMs basically hallucinate because output is not deterministic, and LLMs only pick the next best word based on the existing input. When the phrasing is common, it has a higher chance of hallucinating since there are more options for the next word. And this is why it's very important to fact check everything that you have as output for LLMs, because you really don't know if the next word is correct or not. It's basically doing a pattern recognition scheme where it looks at the previous words to get the next word, and over time it builds a full response. However, it doesn't know when it hallucinates, so it's your job to double check to make sure you notice a hallucination and catch it before you add it to a report or add it to a blog article that you shouldn't be making a mistake on. It's very important to just double check, and that is something that I cannot stress enough. So this is it for transformers. Let's go on to the next section. Now let's cover the basics of prompt engineering, and this is referenced from Dare AI's online guide for prompt engineering. So what is prompt engineering? It's a relatively new discipline for developing and optimizing prompts to efficiently use large language models for applications of research topics. And as previously covered, LLMs are large language models, which is the technology that Claude and ChatGPT are based off of. And prompt engineering skills can help better understand the capabilities and limitations of LLMs. Researchers can use prompt engineering to improve the capabilities of LLMs on a wide range of complex tasks, such as question answering and arithmetic reasoning. And developers can use prompt engineering to design robust and effective prompting techniques that interface with LLMs and other tools. So one of the first use cases of prompt engineering is text summarization. And text summarization is a natural language generation technique that summarizes a large body of text into a smaller, more concise answer. So it can include many flavors and domains, and it is a very basic application of LLMs. So an example is explain antibiotics is a prompt, and the output is a 4 or 5 sentence response that covers what antibiotics are. So what exactly happened here is that the A: is an explicit prompt format that's used in question answering. It is used to tell the AI that there is an expected answer. But right now, the response that we got before is very verbose. So let's go ahead and see if we can shorten it a little bit more. And example 2, we provide the previous response and ask it to explain it in 1 sentence. And the output is antibiotics and medications used to treat bacterial infections by killing the bacteria or stopping them to reproduce. And this is a very short 1-sentence response. So what exactly happened there is that we provided the prompt, explain the above in 1 sentence. And because of that, it compressed the information into a format that's 1 sentence long. So another use case is information extraction. And while language models are trained to perform natural language generation, it's also very capable of doing very basic NLP. And NLP here stands for natural language processing. An example of an NLP prompt can be the following. So we provide it with a sentence or a paragraph of information. At the very bottom, we provide a prompt of mention the large language model-based product mentioned in the paragraph above. So this is a format of requesting information extraction from a given paragraph of information. And the output is a large language model based on the product mentioned is ChatGPT. Let's go back and see if we can find this out ourselves. So we can read here that the authors used AI technology such as ChatGPT in preparation of their manuscript analysis, and in the case as LLM. So basically, if we read this ourselves, we would be able to extract the same information. However, the LLM, in this case, Bard or ChatGPT, was able to extract the information for us. So this is already very useful, even though we can enhance it. This is already usable by a lot of applications. Another use case of LLMs is answering questions, and the best way to get the model to respond to a specific question is to improve the format of the prompts. A prompt can combine instructions, context, inputs, outputs, and other indicators to get improved results. And while the components aren't required, it becomes good practice because the more specific you are, the better response you're going to get. So let's look at an example of this. So in this prompt, we're asking, answer the question based on the context below. And this is a context which is talking about a race of a drug that goes back to New Jersey as the founding, and they generated a early version of it called OKT3. So the question is, what is OKT and where was it originally sourced from? And then we provide an answer. So the output is mice, which is context obtained from nature. And in this case, it's retrieved from this previous paragraph and also from other information that it might have before. But it's able to retrieve the output because we provide this question answer prompt format. So this is another way that you can retrieve information from a input using GPT and LLM models. Another use case, and the last case we're going to look at, is code generation. So one application where LLMs are actually pretty effective is generating code. An example of this right now is Copilot and other forms of generative AI coding applications. So let's try a few prompts. So the first one is providing a comment, and it provides a request, which is ask the user for their name and say hello. And then it outputs a piece of code, which is named prompt was their name, console log, hello. So you didn't even need to specify the language. It sort of assumed it. But there are ways of improving this even further if you specify the language that you wanted to print out or provide more concise comments about the request for code. This covers our section on basics of prompt engineering. Let's now talk about zero-shot and few-shot prompting and the differences in how to use each one. So monkey see, monkey do. So far what we learned about LLMs is that they are trained on a vast amount of data and build assumptions of the world based on that data. When we query an LLM without example, we're using its pre-built knowledge of the world to answer the prompt. And when we do provide examples, and we're guiding the LLM to learn from new information. And the first type when we don't provide any examples is zero-shot prompting. And the second one when we provide examples is few-shot prompting. So zero-shot prompting, LLMs are capable of answering prompts with 0 shots. This is meaning providing a prompt without any context. So for example, if we provide a prompt, classify the text in a neutral, negative, or positive. Text, I think the vacation is okay. Sentiment, which is what the answer we're expecting. The output is neutral. This is based on the knowledge that the LLM already has about the world. And then it provides a response which is neutral because it understands that the vacation is okay is a very neutral prompt. So, as said before, the LLM already understands about the world, and we're using that knowledge in order to get a response. Few-shot prompting, on the other hand, is providing examples in order to get a response that we might want based on things that the LLM has never seen before. So, in the example, a wetpoo is a small furry animal native to Tanzania. An example of a sentence that uses the word wetpoo is, we were traveling in Africa and we saw these very cute wetpoos. To do a fardoddle means to jump up and down really fast. An example of a sentence that uses the word fardoddle is, and that's the end of the prompt. So now we're expecting an answer in return. But notice how in this prompt, we provided a context that said, if this is a noun, then we can use it as a noun. In this case, fardoddle has become a verb, which prompts the LLM to print out, when we won the game, we all started to fardoddle in celebration. And in this example, if we didn't provide that example of what a wetpoo is, the LLM would have a very hard time because a fardoddle doesn't really exist in the English dictionary, so doesn't a wetpoo. But by providing that prompt, we're starting to teach the LLM that if you see a word that you don't know before, you can classify as a noun, a verb, or an adjective, and you can use it in a sentence appropriately as a noun, verb, or adjective. So from this model, it learned the task from one example, and we can actually expand it to have 3 shots, 5 shots, or more shots, maybe even 10 shots. There are a few limitations of few-shot prompting. However, few-shot prompting works for many tasks, but falls short on really complex reasoning tasks. For example, if you work with numbers. So the prompt might be the odd numbers in this group add up to an even number. 15, 32, 5, 13, 82, 7, 1. The answer is, the output is from the LLM, yes, odd numbers in this group added to 107, which is an even number. However, 107 is not an even number, and the LLM started falling short because it doesn't really understand the meaning of these numbers. It just understands that these numbers exist next to each other. The addition also doesn't work. It's just predicting the next word as covered in the transformer section. So in this case, we wouldn't be able to do few-shot prompting because there's no really way of building a pattern around this. It's just understanding the rules of even and odd as well as addition. So notice how there wasn't a perfect answer. This highlights the limitations of few-shot prompting. To answer this, we're going to have to provide a lot more advanced prompting techniques that we won't cover in this section. So that's it for zero-shot and few-shot prompting. Let's go on to the next section. Now we're going to cover how to evaluate models and prompts. What are evaluations? An evaluation, or an eval, in the context of prompt engineering is the process of evaluating an LLM's performance on a given prompt. Evals are good to access a model's knowledge of a domain or capability of a given task based on the prompt provided, and it's very useful for checking the difference between model generations as well as prompt versions. This is important to iterate on prompts, and it provides an empirical score to judge whether a prompt has improved the output or degraded the output. So you can see here that the eval acts as a black box, and the model and prompt goes in, and out comes a score number. So what are the components of an eval? You have the input, the golden rubric, and the model response, as well as an eval score. So this is from an Anthropic slide. For example, if we were given an input like, give me a delicious recipe for cornbread, the output would have the ideal recipe, and the rubric would be the grade on how to assign a score to this output. So for example, we might want to check if it has a mixing tool, might want to check if it has the ingredients, might want to check if it has the instructions. And all these are different parts of the response that need to be there in order for it to be a good response. So then once we have this rubric in place, then we can start iterating on the prompts confidently, because every time a model outputs something, we would be able to evaluate the score. So an example would be the LLM outputs ingredients as well as the tools needed, the time, and then we would evaluate it based on the rubric here. And for example, here it says it doesn't include the ingredients, does include the mixing tool, and then we give it a 9 out of 10. So this is a good prompt. And then we can use that as a baseline to continue iterating. So this is a process of iteratively improving the prompt over time in order to make sure we have the best prompt for our application. So there are different types of evaluations. The most simplest one is a multiple choice question evaluation. This is an easy one to automate because the output is going to be a letter, and then we can just match it if it's the correct letter. So for example, if the prompt was how many weeks are there in a year, we can add multiple choice answers like 52, 57, 50, none. And then if the LLM outputs A and then matches our correct answer, then we can judge that prompt as being correct. So this is very binary. It's a yes or a no. There's no middle ground. So it's very easy to automate. Another type is exact match or string match. So these are meant for judging outputs for open-ended questions. There's more margin of error for string matching to be incorrect. So for example, we can ask it, what is the white powder substance used to make bread? And the LLM response could be flour. The correct answer is flour. And then if the correct answer is equal to the LLM response, then we mark that as correct, which means it's a good prompt. And then these are also very precise, so there's less room for error. However, the LLM could output the incorrect word, and then it could be a smelly mistake, so there would have to be some fuzzy matching. This is not as cut and dry as the open-ended or the multiple choice question evaluation. The last kind is the most complicated kind, and it's a rubric-based open-ended evaluation. And this is good for advanced knowledge prompts that require a lot of output. For example, providing instructions or asking the process of how to do something, maybe booking a trip or like answering questions about travel can be used with this rubric response. And it requires another entity to process the response. And this can be a human or another LLM. How this works is you provide a prompt, like an open-ended question, like how do you make a chocolate cake? And then we respond with an LLM response. And then based on the rubric, for example, the one that we mentioned 3 slides prior with requiring mixing tools and ingredients, we can grade it. Like, for example, if it has butter in the response, then we can add 1 to the score. If it has flour, add 1 to the score, etc., etc. And then over time, we can iterate on the prompt that way because we have a way of judging what is the correct answer of the correct answer components. That way we can build a empirical score out of that. Some evaluations are better than others. Generally, open-ended evals are less desirable because they require human judgment and they're much harder to scale at large volume. They're good for answering and judging complicated prompts, but they do require more work to maintain. And even if you use another AI to judge the responses, it still requires more overhead, whereas simple and detailed evaluations are much easier to evaluate because they're either a single letter or a single word that makes it very easy to match. That covers evals. Let's move on to the next section. In this section, I intend to provide a framework for how to write good prompts. And we're going to cover parts of a prompt and how to structure and test your prompts for production. So there are a lot of things you can do with the prompt, and this is a list of 10 basic parts of a prompt that can be used for generating output. For example, you can provide context to your question, provide the tone, provide background data, images, and PDF, give detailed task rules and descriptions, give examples of the output, provide a history of the context, provide immediate task descriptions or requests, make the model think step by step, and dictate output format as well as pre-fill responses. So this is half of what we covered, and I'm going to cover the second half in the next slide. So for example, the first 5 are context, tone, background data, detail, task description, and rules and examples. And you can see that the prompt that might be generated would contain all of these different items color-coded. So for example, for task context, you provide the context for the AI, such as you're an AI coach named Joe providing created by a company, etc., etc. You provide the tone, which is friendly and customer service. You provide background documents such as a guide, and you wrap it in guide HTML tags, XML tags, and then you can provide rules such as always stay in character, do not repeat the question, etc., as well as examples. And as a continuation, you can also provide conversation history, immediate task descriptions or requests, thinking step by step, which is providing, forcing the model to move a little slower to provide a more accurate response, as well as output formatting, such as putting your response in XML response tags, which makes it easier to parse. You can also pre-fill any responses if necessary, but this is optional, so you don't really have to do this. It's more to lead the AI to put out a response that you expected. So this is sort of a structure for how you can provide a prompt. So for this example, if you wanted to modify this to hypothetically be a customer service agent that is meant for a different company, you can keep a lot of the parts the same. You can change the context, change the tone. For example, maybe you want to be unfriendly instead of friendly. You can change the background data to be something specific to your company. You can provide different rules, like maybe you want to ask the AI to always try to sell something, or maybe try to get the customer to return later. These are all things you can put in the task description and the rules. Different examples could be examples that are related to your company. Conversation history might be different per user. So you might want to keep a context of the conversation and provide that to the AI agent every time you interact with a different customer. Thinking step by step is optional. You can always take this out. And you can change the output format to maybe something like JSON instead of response XML tags. So this is a overall framework for how to approach building a prompt and how to make sure you have a prompt that covers everything you might want to do with your AI agent. So there are steps to write a good prompt, and you can use this as a framework for how to improve your prompts and iterate on them. So the most important thing is to write tests and evaluations and iterate very often. The step 1 would be to create test cases for your prompt and provide edge cases. Step 2, provide a preliminary version of your prompt. This is like a draft 1, and it's something that you can iterate on, but you can start getting evaluations immediately. You can test a prompt against test cases, refine the prompt, and then repeat steps 3 and 4 until you have a prompt that you feel is production ready. Then test against other evaluations and then ship the final prompt. So this is sort of a visual representation of the process. So you can see first develop the test cases, create the first prompt, and then keep on testing against your evaluations or your test cases and refine it. Finally, test against evaluations that you don't have in your test set to test the final performance. And then once you feel like it's ready, then you can ship the final polished prompts. Remember to cover edge cases in your prompt. And this is important to write evaluations against it to make sure they're caught in testing. And some of these edge cases might be not enough information for a good answer, bad user input, which include harmful content, typos, off-topic requests, or gibberish, overly complex input, which might make the AI too pedantic or might focus on the wrong thing. No user input at all is also an edge case, and there are more. These are just a basic example of common edge cases. So this covers the section on how to write a good prompt and providing a framework. Let's move on to the next section. Prompt engineering is a way of framing the prompt and training the AI to think or act in a certain way. And typically you can prime it to be a expert in a certain thing, and you can ask it questions that will be typically answered by that kind of expert. So priming is a really powerful way of completely changing the context of your prompt and making the AI responses more adaptive to what you're trying to do. So for example, a prompt that might be more general is something like, write me a cover letter for a job in creative marketing and advertising for a large scale cola brand. So this prompt is very general and it doesn't really give the AI anything to go off of. And I'm using Bard because I personally think this a little faster and it's good for generative AI capabilities. And I think that it is a useful tool that its UI is really pleasant to use. So I'm going to go ahead and ask it this question. And what it's going to give me is something very general. However, if I change the context of this prompt and say something like, you are an expert copywriter and career coach that provides consulting services and improves and drafts cover letters to clients. You help clients land high-earning jobs in various fields. So what I'm doing in this prompt is changing the context of the AI. And by doing so, we can take the same prompt as before and get a completely different answer. So now we take the previous prompt and plug it in. And you can see here that the response is a little bit more powerful and also contains the context of attaching my resume for review. So, dear hiring manager, I'm writing to express my interest in creative marketing and advertising position at company name. And this is similar to the beginning of the previous prompt. And this one goes a little bit more in depth and adds more details that make it more suited for a cover letter. So, for example, another way that we can prime this is, let's say we are a high-level executive and we will try the prompt before doing that and after. So let's go ahead and write a prompt. Help me write a business plan for selling shake weights in the northeastern United States region. This is a very general prompt and it's going to provide a very general answer. So here it tells me that I need to focus on target market, pricing, distribution, marketing, and funding. And then it gives me all the information that I need, as well as what I need to have in my offer. So now let's prime it and say, you are a successful CEO that has launched multiple large-scale businesses that have done successfully, that have grown successfully in the United States and worldwide. Now you are providing consulting services to people that ask for it. So by creating this prompt, I'm basically priming the AI, and now I ask it the same question. And the answer will slightly change because of the priming and because it will provide an answer that is something a high-level CEO would say. So here, the AI now goes more in depth about executive summary, company description, product and services, market analysis, marketing plan summary, management team, financial plan projections, and so on and so forth. So this is something that a high-level executive would write if they were a successful entrepreneur. So let's do this one more time and ask it a very general question, and something like, teach me about Einstein's equation about energy and mass. So this is a very general question, and it will give an answer that is very general. So Albert Einstein's famous equation E equals mc squared is the most well-known equation in physics. It states that energy and mass are equivalent. So it's a very basic answer. Now let us prime it to say something like, you are a physics teacher that is teaching a college level physics mechanics class to a group of freshmen and are a very strict grader. So now by providing this prompt, we're priming the AI to act like that physics professor. And now let's go ahead and type in the same prompt, and now it'll give a more detailed answer that is something that a physics teacher would say. So Einstein's famous equation equals mc squared is one of the most well-known equations in physics, and this is more authoritative and contains more detail. So by providing the context and framing a question, then you can get a more detailed response from the AI. Now let's cover chain of thought prompting and how we can use it to get a more accurate response for logical reasoning and mathematical tasks. So at a high level, chain of thought prompting is getting the LLM to show its work. It breaks apart a complicated concept in smaller pieces by asking the LLM or providing an example to the LLM of how to show its work, and it can be triggered via few-shot prompting or zero-shot prompting. And we're going to cover few-shot prompting first, and it can do so by showing an example. So short responses are more inaccurate. Getting a short answer from an LLM, especially for a math and logical reasoning problem, is less reliable. Getting a longer response can actually be a more accurate answer. For example, if we gave it a prompt, I went to the market and bought 10 apples. I gave 2 apples to the neighbors and 2 apples to the repairman. I then went and bought 5 more apples and ate 1. How many apples did I remain with? In this prompt, it's a very straightforward math problem because we have 10 minus 2 minus 2 plus 5 minus 1. So in the end, we would have 10 apples. However, if we ask this to an LLM, there's a chance that it might answer 11 apples, which is wrong because based on the previous token, it wants to generate a very short answer. However, based on this combination of tokens, a lot of numbers could be right. And the prediction machine just might choose the wrong one. So how can we get around this? We can get the LLM to show its work, and we can do so by providing some context. And context is a combination of the current prompt and previous responses to build a new response from the LLM. When an LLM processes a response, it looks at everything in the context window in order to find a response that it deems adequate. So in this example, this is still using not chain of thought prompting, but we can use it to get an example of context. The first prompt is Roger has 11 balls. He buys 2 more cans of tennis balls, each with 3 tennis balls. How many tennis balls does Roger have? And the answer in a very short way would be the answer is 17 balls. And then if you ask another prompt, the cafeteria has 23 plates, it uses 20 for lunch, and buys 6 more, how many plates do they have? Based on the context of this sequence of prompts, the answer is going to be short and is going to be 9 plates, similar to the answer here, because the previous context provides and dictates the direction for the LLM response. However, if we were to change the previous answer, it would actually change the response from the LLM because now we're providing an example of what we expect as a response from the LLM. So we can give an example by telling it exactly how we want it to respond and what kind of format. So now given this new context, let's say this first prompt is still the same, but in the second response, we provide Roger started 11 balls, 2 cans of tennis balls, and with 3 each is 6 balls. 6 plus 11 is 17. The answer is 17 balls. That way, you provide a sequence for how we want the LLM to break apart a complicated task. And now the second response is actually going to be more similar to this answer. A simple response might be something like, the cafeteria is 23 plates, they subtracted 20 for lunch, and then they buy 6 more. So 23 minus 20 plus 6, how many plates do they have? Now we have a final answer of 9, and it would show the work for it. So the context window provides the example, and if you want to change the response, the easiest way is to change what you provide in the context window. So there are 2 ways of doing this. We just covered how to do it with few-shot prompting. You can also do this with zero-shot prompting via a special prompt called Let's Think Step by Step. And in this example, you see the difference between few-shot and few-shot chain of thought. So in the few-shot, it provides a short answer. However, in few-shot chain of thought, it provides a more accurate answer because it breaks apart the problem and it thinks about it logically. The same way as zero-shot, if we provide the prompt without any sort of example, then it will just output the same thing. And then with zero-shot chain of thought prompting, we provide a prompt, let's think step by step. It provides a very accurate, thought out response. So let's think step by step. Let's go through an example. And we provide the prompt. I went to the market and bought 10 apples. I gave 2 to the neighbor, 2 to the repairman, then went bought 5 more and ate 1. How many apples did I remain with? Let's think step by step. Now that let's think step by step is included in the prompt, and then the answer is going to be very different than what you had a few slides ago. In this case, it provides the answer of 11, but with this new additional step, it actually provides a more verbose answer that gives you the correct response that you're looking for. So with chain of thought prompting, you get the right answer because the prompt leads to a longer response. Now, let's move on to the next section. Now we're going to cover grounding LLMs for increased accuracy. So what is grounding? Grounding caters responses to specific information. And grounding is the process of providing LLMs with a specific use case or data that's not available during the general part of the LLM pre-trained data. So we already know that LLMs are trained on a vast amount of data. However, this can lead to inaccurate or hallucinated responses. Grounded LLMs are given a text base or examples that generate text based on those LLMs. This increases the accuracy of the responses and decreases hallucination. So why grounding? Typically, we think of LLMs as a general wealth of knowledge. They can do general reasoning and are very good text engines. However, they are not completely accurate. We already seen examples of this with GPT, Bard, Claude. They are able to respond. However, sometimes their information is inaccurate or the numbers that to provide are completely wrong. They're also trained up to a specific time. For example, September 2021 for GPT 3.5, and any new information is not available. So grounding acts as a way of providing that information to the LLM to get more up-to-date and accurate responses. By grounding, we can use them as text engines to extract relevant information, and we can also give them sensitive data like corporate files that might not be available in the general LLM model or might not want to be available in the general LLM. The normal process of grounding is called retrieval augmented generation, or RAG, and RAG gets information relevant for a text and then provides the LLM it as a prompt. Another thing that I should mention is that fine-tuning is another common example of improving the accuracy. However, it's not completely the same as grounding, and it only leads to a 1 to 2% increase in accuracy. Fine-tuning is taking a general LLM model like Llama, which is publicly available, and then providing it new information to cater it for a specific use case. For example, for medical, or legal, or engineering, you can provide it relevant, up-to-date information, and then it can create a new model based on that for that specific use case. However, it doesn't lead to an increase in accuracy that's that significant. Grounding is a much better way of improving the accuracy. So the common use cases are web search and question and answer interfaces. This is, web search is a good example of how to use grounding, since every search result provides completely new information that the LLM can read and process and then provide an answer based on those results, as well as question and answer interfaces, which is based on a large amount of documentation, and then people are asking specific questions of this. Some examples of this is Google's generative search experience for data, Microsoft Bing Chat, Claude AI with their chat with PDF feature, Microsoft Copilot, and Google Duet AI, which goes through your data and provides answers through an LLM interface. So a simple RAG model kind of looks like this. We have two parts, the trigger, the retrieval, and the data source, which is new, and the other part, which is the LLM context, the LLM call, and the output. So typically when you go to a website like ChatGPT or Bard, you can go in and type in a prompt and then get an answer because it calls an LLM call. So this is the general LLM model. However, what we can provide is a information retrieval, summarization, and LLM context building section, which is the major innovation in the RAG model. The core LLM context is built with a prompt query context that retrieves information, and when a user queries or triggers, it gets sent to a retrieval function, which gets information from a database, such as files, database, API call, application data, etc., and then builds an LLM context, which is similar to a prompt, a query context, and retrieved information. This foundational model that we typically use in the backend is something like Llama, PaLM, or GPT. Another way of doing this is called a simple pre-processing model, which takes the previous information that we have already built on, which is the trigger and the LLM interface, which are two components, and adds a pre-processing component. The major difference between the simple RAG model and the pre-processing model is we pre-process information, divide it into chunks, and then store those chunks into a vector database that we can query when we are triggering the new RAG model in order to get the most relevant information to build our context. So this is more of an advanced concept. I'm going to go over it for the sake of completeness. However, you will probably not have to ever interact with this unless you are a developer building an LLM application. So a common process of pre-processing is called embedding, and embedding is a simple term that expresses finding similarities within text. So semantic search is a common way of finding relevant text. However, text is not always written the same way. For example, in the sentence, Obama speaks to the media in Illinois, it's also very similar to the president greets the press in Chicago. However, if you don't have an understanding of language, this is very hard to draw similarities to, because Obama is a different word than the president, the media is a different word from the press, and Illinois is a different word from Chicago. However, we are able to build a large database that finds these similarities, and we can relate Obama to president, speak to greets, media to press, and Illinois to Chicago. Therefore, we can actually determine that these two sentences have the same meaning. This is a common technique that was introduced in early 2018 with models such as BERT, which was released by Google, and has since become a popular way of interacting and training AI. Now, so a technique like this makes it very easy to find meaning with a large pile of text, and in turn, it has turned into a popular pre-processing step in RAG models. So this is an example of how it draws its relationships in 3D space. You can see Obama is related to president, speaks related to greets, and Illinois is related to Chicago, press related to media. So these two documents are now linked. So the limitations of grounding are that the LLM context windows sometimes might be too small to effectively use grounding. For example, context windows are the maximum size of a query that can be sent to the LLM, and it can be between 4,000 characters, 8,000 characters, 32,000 characters, and some even as large as 64,000 characters. If you have too small of a context window, you might not have enough space to actually ground and send a full grounded query. So there are a couple ways of getting around this, such as ranking information and only keeping the most relevant information for the grounded query. And then another limitation is that ordering is extremely important, because sometimes if you order information the wrong way, the LLM won't understand it. A general rule for query LLMs is that if a human doesn't understand it, it won't make sense to an LLM. So if we're creating an automated process for grounding, this is an important consideration to build our grounded query. And lastly, formatting the LLM context can change the output. We typically want to add spaces between relevant information to indicate to the LLM that different pieces of information are distinctly unique. trade-offs. The largest trade-offs in the form of grounding comes in speed versus cost versus accuracy. For those building the tools, such as developers, there's another trade-off of pre-processing versus runtime. However, for most people, this is not something they will actually have to interact with. The biggest trade-off is going to speed versus cost versus accuracy. So by introducing an extra step to the LLM context building, we're building a new LLM query automatically, and this in turn will cause a slowdown as well as use more compute resources. In addition, the extra processing will make tools more expensive, and the benefit you get is greater accuracy from the queries. However, this accuracy can actually be decreased based on the ordering and the relevance of the pieces of information. So this is not 100% guaranteed. This still relies on improving your ranking as well as your ordering algorithms. And then for developers, there is a question whether we should pre-process the data or perform it at runtime. Performing at runtime makes every LLM query more expensive. However, pre-processing is a good way of doing all the work up front. However, by pre-processing, we won't be always getting the most relevant information, and we can only use information that we have processed. So this is the difference between the RAG model and the pre-processed RAG model. This covers our section on grounding. Let's move on to the next section. In this section, we're going to cover multimodal LLMs. What are they? What are their limitations and their use cases? So at a high level, multimodal LLMs are very similar to the transformer architecture that we've learned in the previous section. And they uses the transformer model as well as the input, the prompting, and returns a response. And it adds new modules that allows it to process images, audio, video, and other forms of media. So as you can see in this diagram, this is a basic multimodal LLM model, and you can see the large language model section at the very top grouped together with the image tokens, audio tokens, and video tokens, and instruction and response. And this is now dubbed the cognitive module. This is the basic input and output process that we use with other tools like ChatGPT and Bard. And it takes input, which we've traditionally used as text, as well as an instruction, which is a prompt, and prints out a response. What multimodal LLMs innovate on and introduce are different modules, such as the alignment module and the modality module, that allows the multimodal LLM to input different formats of media, such as image, audio, and video, and align it into the same cognitive space that the LLM recognizes to transform it into different tokens that the LLM can understand in the form of image tokens, audio tokens, and video tokens. Traditionally, these tokens have only been text. And something that is missing from this image is that text is also a token. However, text does not require any sort of reconfiguration. It gets inputted and it gets understood by the LLM model and it gets outputted. However, since images are more ambiguous than text, it requires some sort of reconfiguration and realignment, as well as audio and video. And adding the alignment and modality module allows the LLM to be able to process these different media formats, transform it into a common token that is understandable by the LLM, similar to how text is understood, and then takes that new token input as well as a prompt and then creates a response out of it, similar to how the previous system worked. So the main innovations here are the alignment module and the modality module. So multimodal LLMs exist in the marketplace already. They are not just a theory. There are models on the market such as Cosmos by Microsoft, Palm-E by Google, and GPT Vision by OpenAI that allows you to input different media formats and have it be understood by the LLM model and output with a response based on the input. You can also see products like GPT Vision as part of ChatGPT, as well as Bing Chat, use and have multimodal capabilities that let you process images. You can input an image and ask the LLM to understand what's in the image and then output a response based on those inputs. So these products are on the market and you can play with them to understand how they work. So let's talk about some of the advantages of multimodal LLMs. One of the advantages is improved accuracy. Multimodal LLMs can achieve higher accuracy on tasks that require multiple forms of data, and they can better understand the context based on a conversation because they can, for example, use facial expressions as an input. They can also use tonality as an input from audio. These are different ways that these LLMs can get clues of the conversation based on the way that it's spoken. Another advantage is that multimodal LLMs can be used for new applications. Like, for example, they can be used for creating captions for images and translating spoken word from English to a different language. And it can even create art because it can take images as an input and create images as an output. It can also be used for more natural interactions. Multimodal LLMs can interact with humans in a more natural way since they can understand the world through different forms of senses, such as audio, video, and images. For example, if you speak to the multimodal LLM in your natural tone, the LLM can understand it and respond based on your tonality and also based on the way you said something. For example, if you speak with a more southern accent, it can understand that southern accent and respond in a southern accent as well. It can also have a better understanding of the world because multimodal LLMs can develop a better understanding through multiple forms of inputs. And this can help it make better decisions based on the data that it sees. The use cases of the multimodal LLMs, some of these are theoretical, some of these are being realized right now. AR, VR is one big use case of multimodal LLMs because through the lens and camera, it can understand parts of our real world and it can understand it and provide responses for those inputs. For example, it can understand signs and might give you instructions to stop, or it can read labels and give you instructions. For example, maybe completing a recipe or putting together different components into a cohesive product, maybe if you're in the grocery store. It can also be used for education because it can create more personalized and engaging learning experiences. It can generate interactive lessons based on images of a student learning a process or maybe based on different parameters of a classroom setting. It can also be used for healthcare for processing patients' clinical work and also identify different potential ailments based on X-ray images. It can also be used for customer service because it can understand voice and it can understand a customer's complaints and provide solutions based on their questions and then also detect their tone to provide a more personalized care experience. So these are all use cases of multimodal LLMs. However, they still have their own limitations. Some of these limitations include processing images and audio is more ambiguous than processing text. So data quality and interpretation problems might cause multimodal LLMs to be less accurate than a human. It's hard to capture that kind of data accurately, and the data that a multimodal LLM gets, it can only provide a response as good as that data. So if the data quality is not good enough, then the multimodal LLM might provide less accurate answers. And multimodal LLMs are still subject to bias based on the images that they're fed and might not have an accurate view of the world. So that covers our section on multimodal LLMs. Let's move on to the next section. So we've covered a few lectures about the transformer model, and let's take a deeper look at how LLMs process prompts. So just a warning, this is a deeper dive. If you're not interested in understanding LLMs at a deeper level, you can skip this lecture. And this only goes into the deeper mechanisms of how LLMs understand human text and processes. You don't need to understand this to use generative AI effectively, and it's only for people that are interested in learning more about the encoder model and prompt processing. So let's go back to the paper that Google published in 2017 called Attention is All You Need. And attention, let's mathematically define it, or let's concretely define it, is a mathematical representation that allows LLMs to understand words used in different contexts. An example of this is the shirt is very cool versus is cool outside. Cool is used in both sentences but has different meanings. Cool in this sentence might mean a showing of enthusiasm, and cool in the second sentence represents a temperature. This is very important because it's always been difficult in AI and machine learning to understand the same word used in different sentences because the meaning completely changes based on the other words around it. And that's in a very important note is that the words used in the sentence completely changes the meaning. So a word converted to a mathematical representation should have a different weight based on the other words in the sentence. So take a look at the mathematical embedding of the sentence, the bank of the river. So here, bank could have two meanings. Bank could mean the side of a river. It could also mean a financial institution. So if we change this into a mathematical representation here, the bank would actually change based on the other word that is of relevance here, the river. So these two are important and the relationship between them are important. So we can add a 0.9 to the bank and a 0.1 for the river. Following, we could also add a 0.1 for the bank to the river significance and a 0.9 for the river. This is important because the current word is more important than the words in the sentence that are to the side. So another example is the money is in the bank, and this is a financial institution use of bank. So the two main important words in the sentence are money and bank. So therefore, they're relevant. Both of these words are relevant to each other that they're in the same sentence, and we should give it a different weighting respectively. So we can give a 0.8 weighting for money in the first word and 0.2 to bank, and then a 0.2 for money and a 0.8 for bank. So the final result of these sentences are that they have unique weightings that make them unique in their understanding by the computer, as in the computer understands this differently. And fun fact, this was meant to be used with Google Translate because language translation has this problem happen a lot. So let's clear this. And how does this all work? So to understand this, we need to understand neural networks. And neural networks, let's define it, are mathematical representations of how a human brain is structured, with neurons being independent nodes connected together by edges with weights. And you can see a visualization of a neural network here. The nodes are independent neurons, and then they're connected to each other via edges with weights, with a final output layer, which is the final result of the neural network. During training, these neural networks are trained to reach a certain goal, which is the output. And the training data is tested against the output, and what you're testing are the weights between these nodes. So the weights are randomly selected in the beginning, and in each iteration of training, the weights are adjusted to get closer to the goal. So for example, if this weight had 0.2, we might test it and see if the 0.2 is a good weight. Otherwise, it might change, and then it would become hypothetically a 0.3. An interesting point of this is that in neural networks, we don't necessarily need to pick the neurons or the nodes. The system will find the optimal amount of the optimal nodes and the optimal weights through a process that we're going to cover on the next slide. So it does this training through a thing called epochs. And an epoch is just an iteration of training. And in each epoch, the weights are readjusted and the neural network attempts to get closer to the final goal of identifying the object. And this process is called training. When we get to the point where the neural network can't get more optimized, then we reach the stopping point. And the process of getting here is called gradient descent. So if you imagine a training as like a ball going along this ramp, every training cycle, we're going to try to get closer to the bottom because that's our goal. And then if we overshoot, we just need to readjust the weights until we repeatedly get closer to the minimum cost. And then once we reach the lowest point, then we reach the final point of training and we have a optimal neural network to the best of our ability. And I say best for the ability because the weighting and the performance of a neural network very much depends on the training data and the process done. during the training. So now that we cover neural networks, we can get to encoder and decoders. So encoder and decoders are a fundamental building block of a transformer model. The transformer model transforms things from one thing to another, and the encoder and decoder work together tangentially in order to accomplish this. So an encoder model takes the input text that a user might add. In this case, it's your prompt. And then it feeds it through a neural network, which we just learned, into the decoder model. And this encoder model transforms its input into a thing called an embedding into the decoder model, which then does the generation and prints out a final generated text. So a way you can think about this is encoder takes pre-processing and then decoder generates text. So a definition of this is an encoder is a neural network for transforming text into a format that can be understood by a computer. This is also called embedding and is fed into the decoder model. The decoder we already learned in the previous transformer lecture. Our neural networks are good at generating text and uses the input of an encoding as attention to know where to begin outputting the text. Decoders are autoregressive, which means that the output is fed back into the decoder until a special stop character is reached. Remember the transformer lecture when we went through a few examples of how that decoder works? GPT is a decoder. Think of decoders as a knowledge base of the chatbot. All the knowledge that needs to be known is held in the decoder, and then the decoder takes the prompt, which is created by the encoder, and uses that to figure out what part of the database to access in order to output the text that's relevant. So how is this relevant to prompting? One thing that's important to remember is that computers don't automatically understand language or even letters. Computer understands numbers, and to get a computer to understand words, you need to convert those letters or words into numbers. So encoders perform the conversion between text to a sparse vector, and it can use it to understand what you're talking about. So for example, here, you can see this text converted into an embedding like this. And this is similar to the embedding that we talked about on the attention is all you need slide. The visual representation of this is an input text might look like the beginning of a longer paragraph, and that is how the decoder model understands what part of the database to access or the saved trained model in order to output text as relevant to your input prompt. So let's go back to attention. During the embedding process, we adjust the weights based on location and the words around it. And during the decoding, the computer works procedurally based on the query presented by the encoder. And since we place different weights based on the sentences, the context can completely change the embedded vector, making them unique. So let's go back to the example of the bank on the river, and the money is in the bank. Because the bank is occurring in the same sentence as river, and we know that these two are not relevant, and they shouldn't be existing in the same paragraph. The subset of responses that contain sentence 1 are completely independent from the subset that contains sentence 2. And because we have the prompt which contains the bank of the river, from this we know we can go to section 1 of the LLM. And then for the second option, because we know money and bank occurs in the same sentence, then we can go to section 2 of the LLM. And this would only be possible if we put it through the encoder model and create these weights, because now these weights are not the same. A computer cannot understand this easily, but it can understand this much easier. And because of this, we can output something that might sound right to the first sentence, the bank of the river. We can say something like the bank of the river has a tree. That doesn't make sense in the second sentence, money in the bank has a tree, because this is more relevant to the first sentence, this is the nature. But the second sentence, it will be, the LLM will know not to decode something in that first set of data for the second sentence because the first prompt does not have the word river. So, hypothetically, if you were to just input something like the bank without of the river, then the input would not know which subset of data to go to, so it has a higher likelihood of hallucinating. So that is an important part of adding as much detail as possible, because the more detail you add, the more likely you'll be able to access part of the LLM that you want to access. So let's put it all together. With a fully trained decoder model and unique embeddings per prompt, the chatbot will be able to create unique responses for each input. This shows that prompting is important since placing more context allows you to get a more specific, tailored response. And adding more words entirely changes the embeddings into the LLM input and allows for a different part of the knowledge base to be accessed. So, as you can see here, this was previous encoder-decoder model, and you can see how it all works together in order to get you a valid output. So, let's take it one step further and think multimodal. We covered this in a previous lecture, and the cool thing about embeddings is that they don't just work for text. You can convert audio, images, and more into an embedding that flows into a decoder model. And for these types of media that aren't just text, you need to just identify the important parts of the media and then create a shared language for the computer based on this. So you can see here the audio gets put through an audio encoder and then creates audio embeddings, and a video gets put through a video encoder and gets video embeddings. So all these can be fed into the decoder, and then the decoder can spit out text. That's how a LLM like ChatGPT or Google Bard is able to understand different forms of media and output text based on them. So that covers this lecture. Let's move on to the next one. Now we're going to cover what is RAG, or Retrieval Augmented Generation. RAG is a process that enhances responses from LLMs and is a technique for enhancing the accuracy and reliability of generative AI models like OpenAI's GPT, Google's Gemini, and Claude's Opus, Haiku, and other models with facts fetched from external sources. It fills the gaps in an LLM's knowledge where it might not have a deeper understanding of a certain context or dataset. RAG enables you to combine internal and external sources. For example, if you have a dataset of internal communications that is unique to your company, this information might not be publicly available to the LLM when it was trained. So by performing RAG, you will let the LLM reference your data, cite it in order to provide a more accurate answer to the user that's querying it. There's going to be a few diagrams later on in the slideshow that will show this process in a more visual way. An important part of RAG is that it enhances user trust. Because LLMs don't necessarily have the information when they are trained, performing RAG provides the LLM with a deeper context of relevant information on retrieval time that provides a more accurate answer for the user. This builds trust by the user because they know that this information that's provided is relevant because it's provided by sources that are similar to the query that they're performing. And an important note is that sometimes data isn't provided in a public setting, so LLMs won't necessarily be trained on it. And there are two options if you are trying to provide private data, which is train your own model, which is expensive and extremely time-consuming, or using a public LLM and then performing RAG, which more often than not is cheaper than training your own model. And RAG can be implemented really quickly. It can be implemented in 5 lines of code using the RAG tokenizer, RAG retriever, and RAG token for generation functions inside of the transformer package in Python. A lot of the work is already done, so it's actually very simple to implement. Use cases of RAG. An important model for understanding how to create new use cases is that you are taking a public-facing LLM and you're providing it with private data. So any data that is sensitive is a good candidate for using RAG. So for example, one thing that we can use is medical records, since this is private data, and we provide context to a public LLM for this. We can also provide the user's code base to fix bugs. We can answer customer support questions using internal documentation. We can act like a virtual coworker by resurfacing internal meeting notes and chat logs that the public LLM might not have, and many more. Generally, anything that uses private data is a good candidate of RAG. So this is sort of a visual of how RAG is performed. We have the base model in the center, and then in the top, we don't have any sort of RAG implementation. So we just ask the base model, and the base model responds with I don't have information about this topic. But if we were to perform RAG, which is this section here, that we provide a user data set as well as a vector library and perform some sort of sequence transformation, we can turn this generic LLM into a specific LLM for a use case by using the data that's provided in those data sources. So now when we query it about a specific thing, like what was the name of the movie Chris emailed me about, it can provide an answer because it now has this information from the database. The process of performing RAG is keeping sources in a data store. This is your library that you get new information from based on the user's query. Then we query the source for relevant sources. We create an embedding, which is converting that text into a format that the LLM can process and put it into a vector database. We query the LLM with the embeddings that we retrieve from the data source, and we get the response. A visual representation of this is here. You can see the user queries enterprise app that performs the user query. And then on the other side, we retrieve the data from a knowledge store. We get the documents, we put into the embedding model. We convert these into an embedding, which an embedding is just a numeric representation of the sources and underlying documentation. We put it into a vector database, which is a ML-specific database that makes it fast for performing ML queries. And then we take the prompt, put it into the LLM, and get the response and give it back to the user. So this is a high level of how RAG is implemented at a system level. A thing to remember about RAG is that current sources are better, equals better performance. You should keep your sources up to date because, RAG depends on the sources that you provide. If you provide bad sources, the AI is gonna provide bad answers. So keeping your sources up to date with some sort of system is incredibly important to do so. And you can try it using a tool called Notebook LLM provided by Google. This is a user-facing interface that lets you provide your sources into an LLM model, Gemini, to do some RAG analysis. Other sources of RAG that is in the public marketplace right now is AI Overviews by Google uses RAG based on search results. Gemini uses RAG based on search results for web searches. OpenAI uses RAG based on Bing searches. Meta AI uses RAG on search data. And other sorts of file uploads. When you upload a image or a PDF to OpenAI or Gemini, that performs RAG as well. So these are some open current implementations of RAG on the marketplace. If you want to try it on your own documents, please check out Notebook LM, and you can play around with it to see the RAG process and what kind of results you can get by performing RAG. That covers this lecture. Let's move on to the next one. A new architecture came out recently for building AI agents called Model Context Protocol, or MCP, and it has reached wide adoption within the industry, and it's worth going over in a refresh lesson in this course. So what is MCP? It is the USB-C for AI. It's an open standard to facilitate seamless integration between AI applications. It can be between AI applications and different platforms. For example, you can have one application developed by company A, and then it can be used by company B, and they don't have to know about each other. It's an open communication protocol that prevents vendor lock-in. It leverages communication between LLMs and external sources where data lives and applications can be applied. And it was introduced by Anthropic in November 2024. It was supported by Google and Agentspace in their recent Cloud Next 2025 keynote. So here are some core concepts. I'm going to go skip ahead and show an image just to ground our conversation in the following slides. So here you can see the MCP architecture. Think of it as a USB hub. You have remote data services plugging into the hub. You have local data sources also plugging into the hub. And then MCP clients, which will put it all together and then send it to the MCP hosts, which are the AI models. You can use any AI model here. And this picture is just OpenAI and Claude. However, you can also put Gemini and other sources in here. And this performs the actual execution. So let's go back and talk about the core concepts. You have tools, which are the actions or functions which the LLM can decide to execute. These can be verbs like create ticket, get forecast, query database. These are like the APIs for the LLM. You have the resources, which are the data sources that plug into the MCP protocol that the LLM can access for retrieval or context. These are like files or databases and logs. You have prompts, which are the user-controlled part of the MCP protocol. These can be reusable templates or workflows or external prompts introduced throughout the system. But these are the guide rails for how the MCP executes and what data sources or parts of or context gets retrieved. And then you have sampling, which is a feature where the server can request an LLM completion from the MCP hosts, and then it's the actual execution of the LLM query. So think of it as a switchboard. The prompts are the guidance, the resources are the context that is inputted into the an LLM prompt, and then the tools are the interface of the LLM MCP context. So when you kick off a tool or a tool is used within different LLMs, it kicks off a chain process which executes the action. So the key architecture, it uses a client-server architecture with an intermediate host process. The host is a primary application where the user interacts with the AI chatbot. This is where the user interfaces with the MCP. The client, which resides in the host process, maintains a dedicated communication between the host, the server and the host. And the server is the program that wraps the external system, data sources, and utilities. This is the wrapper around everything. Communication between parts are using JSON RPC 2.0. These are just RPC calls using JSON encoding. There's two types. Standard I/O, which is when the server and client run on the same machine, and server-side events, which is typically known as regular API calls using an HTTP host. So now we're back to this image. Now hopefully this draws a little bit more of an idea of how MCP works. Let's say you have various different data sources you need to use to make your LLM call work. You plug it into this bus. The MCP server with local data sources are also plugged in. And then this will, when an external action comes in, the prompts will guide what data to retrieve from the remote services, stitch it together, send it to the host, and then the host will execute the LLM query. So here's a use case that MCP is good for. Automated report generation. Imagine generating background checks, and it requires various data sources from many siloed data streams in government computers. MCP acts as a connected glue that requests relevant data sources from data streams from the data sources and glues those together. And then it acts based on the current client request and formulates for relevant data calls to get data for a subject. Once it retrieves that data, it follows user prompts and stitches it all together, sends it to an LLM, and puts together a comprehensive report. Another example is a development tool that references code databases, code repositories where different project files are siloed. Imagine these data sources are indexed, and then the MCP protocol will be used to request relevant data sources when a query is executed. For example, if a person requests suggestions about criteria of a subset of features, MCP can request those features, those functions from the index data sources, and then stitches it together and sends it to the LLM for execution. So the possibilities are endless in agentic systems because MCP is a foundational technology structure for capable AI agents. The beauty of this is that because this is a standardized system, you can stitch AI agents together. So if you have one AI agent that's dependent on another AI agent, the MCP protocol allows you to remote procedure called other AI agent to perform an action and then return it. So these are like the building blocks, the interface of building blocks between different AI agents. They're like the Legos, standardized Lego circles where you can stack other Legos on top. You can use it for workflow automation. AIs can use MCP to perform multi-step workflows like data retrieval, analysis, report generation, and email sending. There's task execution, which AI can perform tasks in the task manager, and manage cloud infrastructure, or even control 3D modeling software. And it can also maintain context between different tools and different data sets, which is crucial for more complex tasks. So another type of protocol that is popular is retrieval augmented generation. Here is a pros and cons of the MCP versus RAG. You can see the MCP is a standard integration, while RAG is information retrieval. And then mechanism is more structured in MCP. There's two-way data reads, whereas RAG is one way. The standardization is very high. And it is high control versus low control in RAG. Another one is direct API, which was popularized by OpenAI in the past. This is deprecated in favor of MCP because MCP has high standardization. The architecture is very defined, high interoperability between different AI agents, and the control is high while the growing ecosystem is getting bigger. So the key adopters are Anthropic, which is a major AI lab, OpenAI, which is also a major AI lab, Google, a hyperscaler and AI lab, Microsoft, Block, Cursor, Replit, Codium, Zapier, N8N, Apify, and much more. So to integrate it into your application, you just use an MCP SDK, you implement the core logic, define the MCP primitives, configure and run, and finally test it. So this covers there's plenty of guides on how to do the integration. I recommend looking for one online. There's plenty of good resources for that. So this covers the MCP section of this course. Let's move on to the next section. We've talked a lot about the LLM products that are currently on the market, as well as under the hood how LLMs work, as well as the underlying technology of transformers. Now let's cover generalizing your LLM knowledge and applying the principles that you learned so far in this course to new chatbots that are on the market that you might not have worked with before, and chatbots that will enter the market in the future. Right now, there are a ton of LLM-based chatbots out there, and some of them we might work with in this course, and some of them we might not. Examples of this are ChatGPT, Google Bard, Microsoft Bing, Claude by Anthropic, as well as Grok, which is a new one by X or Twitter. And there are some principles that you can take with you for all these LLMs and any future LLMs that might come out on the market. The general interface for prompting these LLMs are very similar. They typically have a chat box that lets you type in commands, also known as prompts. And prompts are similar to a keyword search on a search engine. However, it's important to remember that hallucinations do happen on LLMs as of now, and it is not a solved problem. So it's important to not treat these as knowledge graphs, but treat them as a creative way of getting a response that might be correct and might not be. They are a good way of saving a lot of time when you're working with more free form and creative expressions, such as writing or drafting. However, they are not good for things that require specific and very correct answers, such as law, medicine, and those kinds of subjects yet. And learning prompting skills can carry over easily to other chatbots, since they all use a similar underlying technology, as well as share a similar data set, as well as have a similar interface. Prompting principles to remember: be as verbose as possible. You want to talk to the chatbot as if you're talking to another human being, and you want to provide clear instruction and clarify how you want your response to be formatted. You can provide guidance in these responses using techniques that we cover like one-shot or multi-shot prompting. And there is an important key phrase to remember. It goes, take a deep breath and think about this step by step. This has actually been proved by Google research that this will improve the responses for logical tasks that involve things like math and logic. And use chain of thought prompting to build context to get more specific responses to your questions. LLMs have a very similar knowledge base, and this is to show the commonality between different LLMs. Most LLMs that are available on the internet are based on a similar data set, and this data set is most commonly provided by a nonprofit called Common Crawl. Common Crawl is focused on providing a shared search index, and some companies might have specialized data sets that make their LLMs unique. In the general case, the base core knowledge for these chatbots come from the Common Crawl index. However, sometimes walled-gardened platforms such as Google, Bing, Facebook, and Grok might have their own unique data set that makes their chatbots a little bit different than the others. But the shared data is typically gathered from the internet. And the major difference between LLMs are the weights between the nodes in their neural network, which is underlying technology, as well as the human feedback that collects from the people working on their platform. As people interact with the chatbots, typically there is a feedback mechanism that makes their responses better and teaches the chatbots how to respond better to users. So overall, a lot of these chatbots are similar, and the data is very portable between them. So with this, we covered the generalization of using your LLM knowledge. You can use the same principles you learned in this course for any product on the market and any product that will be coming out on the market in the future. Hallucinations are a natural byproduct of LLMs because of the way that transformers work. Now let's cover an instance where hallucinations have gone wrong in the field of law and what happened. So this is citing an example of what happened in June of 2023, about 6 months after ChatGPT was released and became popular. And this happened in a federal court in New York. A lawyer, Stephen A. Schwartz and Peter Loduca, used ChatGPT to generate a legal brief for a lawsuit against Columbia Airlines Avianca for an injury on a 2019 flight. Schwartz used ChatGPT to perform legal research, and ChatGPT created fictitious cases that didn't actually exist. When the Judge Castell, read the legal brief in court, he was surprised with the legal citations because nobody had knowledge of them and they didn't exist. Avianca's lawyers called them out on this. We're talking about the Southern District of New York, the federal district that handles the big cases, 9/11 to all the big financial crimes, Shin said. And this was the first documented instance of potential professional misconduct by an attorney using generative AI. This happened in a major court in New York that handled many large cases in the past. So whose fault was it? Schwartz told U.S. District Judge P. Kevin Castell that he was operating under a misconception that this website was obtaining these cases from some source he did not have access to. So he thought that ChatGPT knew about these cases and nobody else has ever heard of them. Schwartz used ChatGPT to generate the text, and Loduca, another lawyer, signed off on it. Because Loduca is higher up than him, by signing off on it, he indicated that he has read and verified all the information in the legal filing, but he did not actually verify any of this information. They were potentially at risk of being disbarred, which means losing your legal license. And was it ChatGPT's fault, the lawyer's fault, or both? What was the outcome? Both lawyers were fined $5,000, and the judge ended up crediting their apologies and their remedial steps to explain why harsher sanctions were not necessary. There was a risk of losing your law license. If you do not have your law license, you cannot legally practice law in the United States. So this was a big deal and potentially detrimental to their career. They also face extreme embarrassment because they basically showed and made a public spectacle that they do not do research and were presenting information that was not true to a judge as well as other lawyers. It was essentially fraud, and it could have been misconstrued as bad faith. However, it was just counted as negligence. So how could this have been avoided? Shorts could have avoided this by double-checking all the information generated by the chatbot. Laduca could have avoided this by double-checking the work done by Shorts. Shorts could have mitigated the impact by grounding the LLM and making sure it uses references that are accurate. Shorts could have avoided this by using a search engine to perform the research and his own judgment. And it's important to remember that LLMs can hallucinate. The information that is retrieved can be correct, but it could also be completely made up. LLMs are not knowledge graphs. They simply regurgitate information. So the information that they regurgitate could probabilistically be true, but it could also probabilistically be garbage. And in this case, unfortunately, it was a public spectacle that the LLM generated information is garbage, and these two lawyers were potentially in for a very large punishment. However, the outcome ended up being pretty light. However, this is something to take caution about if using LLMs for work that is very correctness sensitive. If it's something that requires a lot of precision, it's recommended to spend more time double checking the output.